The 1914 Nobel Prize in Physics went to this man, Max von Laue, who won the prize for his discovery of the diffraction of X-rays by crystals, which is very important scientifically, and we'll get to that in a minute. But he actually had contributions far beyond that. Let's talk about that in a second. Before we do, please click that subscribe button. Go ahead and click like on the video. That actually helps us gain a larger audience. So Max was actually a contributor in things like optics and crystallography and quantum theory and superconductivity, theory of relativity. He actually helped Einstein get that theory of his, which was written in 1905, accepted by the wider community, because at first it wasn't necessarily where people looked at it and went, oh, hey, this is it, right? That wasn't the way it worked. It took time for that to gain acceptance, and Max was one of the people who helped that happen. In between World War I and World War II, he was actually a very strong objector to Nazism, and after World War II was over, he actually helped re-establish and organizing the German scientific community into something that was more coherent than just this fractured thing that was around after the war. So yes, he was a Nobel Prize winning scientist. Yes, he had great contributions, but he also had contributions far outside the scientific realm that were very important. So where did he come from? Did he just magically appear one day, or did he actually have some kind of background that got him into this? Well, let's take a quick look at that background. When you work on a PhD in physics, at least in my time period when I worked on mine, you have more than one advisor. You have a committee of people who oversee your work and kind of give you help and mentorship and teach you things. Well, one of the people who he had as a teacher for his doctoral work was this guy, Max Carl Planck. Now, that name, if you're a scientist or a physicist or a chemist, is you just know who that guy is. He did all kinds of work. Most interestingly, he did go on to win the Nobel Prize 4 years after his student did. So he won the prize in 1918 for his work in quantum theory. He had contributions in theoretical physics, quantum theory. He's considered one of the founders of actually modern physics because he helped revolutionize that understanding of the atomic and subatomic process. He even has a constant named after him called Planck's constant, which is foundational in quantum physics. It was used to drive a set of units that's still used in physics labs all over the world today. But he actually had somebody else on that committee as well that was very, very notable. Meet Arnold Sommerfeld. Arnold here, he did some fantastic work in introducing quantum numbers and azimuthal quantum numbers and third quantum numbers and magnetic quantum numbers. He introduced the fine structure constant. And all of that is a bunch of scientific gobbledygook. I understand. All of that's really complicated stuff. Arnold here never won the prize himself. He made fantastic contributions at a time when we really needed fantastic contributions to forward our understanding of the atomic structure. So what he did was he did a lot of this fantastic work as a theorist, but he spent a lot of his time mentoring students and going on to teach the next generation of scientists how to be in their field. He actually was a postdoc supervisor to 7 future Nobel laureates and supervised at least 30 other famous physicists and chemists who have processes and labs named after them and all sorts of interesting things. So while he may not have ever won the prize himself, his legacy cannot be misunderstood. It cannot be understated. It's fantastic. He was one of a kind. Von Laue didn't just work with people who left a legacy, he left one of his own. Meet Leo Szilard, whose name I just absolutely mispronounced, and I apologize for that. He was a student of von Laue's and worked in many things in the nuclear world. He worked with Fermi, he worked with other famous ones, but perhaps one of the things he's best known for in the physics community is he wrote a letter for Einstein's signature that has become known as the Einstein-Salazar letter, which what that letter said, it was sent to the President of the United States, who at the time was Roosevelt, Franklin D. Roosevelt, warning that Germany might be working towards a nuclear weapons program. That letter led Roosevelt to pour a bunch of money into a nuclear development program for reactors and other things, and out of that project came the Manhattan Project. I'm not sure that the Manhattan Project was the intent of these two when they wrote and Einstein put his signature on that letter, but his mark was left. He was a student of von Laue's. Now let's go back around to the professor and see what it was that he contributed to the scientific world. Now, von Laue's work was for discovering of X-ray diffraction by crystals. And what that means is using X-ray diffraction by crystals, we're able to determine a whole lot of things. So you can determine the phase composition, the crystal structure, orientation of a powder, solid, liquid, gas sample. You can do things to determine the purity of a sample that you're looking at. Is it very pure iron? Is it less pure iron? These things matter if you're building large objects, if you're building large physical structures, if you're building purified anything. If you want to use an absolute sample of something, X-ray diffraction is very important. What else does it do? Scientifically, it proved beyond a shadow of a doubt that X-rays were waves, not particles. It was not a subatomic particle penetrating through skin to take a picture of a potentially broken bone. It was actually a wave, just the same way as light and radio waves work, just with a much shorter wavelength. And before this time, that was not known. So what else is diffraction good for? Where else might you have seen it in your life other than just, a goofy guy talking about it on a science channel? Well, let's take a look. Many children all over the world know the joy of turning their shapes in their hand into shadow puppets on the wall, and you can make those shadow puppets much, much, much larger than your actual hand by holding your hands closer to the light source than to the wall. So you can take your little ability to make a bunny rabbit and make it be a 2-foot tall bunny rabbit on the wall. Well, that's an example of diffraction. It's one of the few joys of being a scientist, one of the many joys about being a scientist, is the ability to take these fundamental things in our daily lives and use the understanding of how those things work to determine other stuff. So one of the things that attracted me to the field of physics was the fact that you got to understand how everything works. It wasn't just, hey, memorize this. It wasn't just, hey, here's an idea, make it slightly better. It was understand the world around you and use that application of that understanding to understand more things. So while it may seem simple that a shadow puppet on a wall is something everybody understands, but how does that shadow puppet work? And if you use that information and then you apply it somewhere else, you may win a Nobel Prize. Everybody have a great day.